Okay, good day. This is Honors Algebra 2. I'm Mr. McColley, and this is the video presentation for section 10-1, sequences as functions. So let's get right to it. Today we're going to relate arithmetic sequences to linear functions, and we're going to relate geometric sequences to exponential functions. And so before we can do any of that, let's take a quick little exploration of some related numbers. And what I'd like you to do here is to just kind of take a pause and see if you can determine what the relationship between these two lists of numbers are. So I'm going to pause for. Okay, so hopefully you paused there and you took a look at the numbers and you notice that if I look at these numbers, every time that I move over 1 unit in these numbers or move over one value, each time here I am adding 3. So 2 plus 3 is 5. 5 plus 3 is 8. 8 plus 3 is 11. And then 11 plus 3 is 14. And then when you came down to this set of numbers, you notice that 2 times 3, should be a times there. I don't know why I'm not getting a good multiply sign, is 6. And then 6 times 3 is 18. 18 times 3 is 54. And then 54 times 3 is 62. So this is two types of sequences that we are going to be talking about here in the next few lessons. So let's have a couple definitions. First, a sequence is a set of numbers in a particular order or pattern. Each number in the sequence is called a term. A finite sequence has a limited number of terms, and an infinite sequence has an infinite number of terms, and the first term of a sequence is denoted as a sub 1, the second a sub 2, and so on. So let's go back to here, and let's talk about these. Both of these dots here means that these are infinite. They're infinite sequences that they go on forever. In this particular sequence, a sub 1 is equal to 2, a sub 2 is equal to 5, a sub 3 is equal to 8, and so on. So the term numbers are those values. In this particular sequence, a sub 1 is equal to 2, a sub 2 is equal to 6, and a sub 3 is equal to 18. So we have some reference of all of those things. Continuing on with a few more definitions. An arithmetic sequence is a sequence where each term is determined by adding a constant value to the previous term. This value is called the common difference. And in a geometric sequence, a sequence where each term is determined by multiplying the previous term by a constant value, this value is called the common ratio. So since here we have added, this thing is a arith sequence, and its common difference is 3. And then here we have a geometric sequence, and its common ratio is also 3. So when you're adding a constant value, you have an arithmetic sequence. When you're multiplying by a common value, you have a geometric sequence. All right, so determine if the following sequences are arithmetic, geometric, or neither. So here's what I would do. I would take the first two and find a difference. So 2 to 4, I would add 2. And then if I add 2 to 4, I don't get 8. So it's not arithmetic. All right. So geometric. What times 2 is 4? Well, 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 34. This thing is geometric. All right. Well, let's do the same thing here. 1 plus 1 is not 1, so there's no common difference here. 1 times 1 is 1. 1 times 1 would not be 2. 1 times 2 would not be 3, so clearly this is not arithmetic or geometric, so it's neither. And then this one, let's see, we add. So what plus 10 is 8? 10 plus negative 2 is 8. 8 plus negative 2 is 6. 6 plus negative 2 is 4. 4 plus negative 2 is 2. 2 plus negative 2 is 0. 0 plus negative 2 is negative 2. This is, since we are adding each time, arithmetic. All right, so in the next page, I take the values of, I think, this geometric one. So the first term was 2, the second term was 4, the third term was 8. So I'm taking the values here. The fourth term is 16, the fifth term is 32, the sixth term is 64. And so let's take this and plot those values. And you'll notice very quickly that we get a curve of discrete values that looks very much like something that we've dealt with before, an exponential. All right. And then if I take that second bunch, this arithmetic sequence, 10, 8, 6, 4, 2, 0, 1, and so the first term was 10, the second term was 8, the third term was 6, the fourth term was 4, the fifth term was 2, the last term was, or not the last one, but the sixth term was 0. If I match those up, notice what we get here. I get a discrete value that looks like a line. So as a conclusion, and that's not necessarily a proof, but it does give us a good idea to know that an arithmetic sequence can be modeled with a linear function, which we will be doing in the next section. And then a geometric sequence can be modeled with an exponential function, which we'll be talking about in section 10.3 and 10.4. All right, so to finish up, just a couple examples here. First example is find the next 3 terms of the sequence. So the first thing we got to do is we have to determine what type of sequence it is. And so if I go, let's see here, from 1 to 5, I would have to add 4. 1 plus 4 is 5. 5 plus 4 is 9. 9 plus 4 is 13. And so this is clearly an arithmetic sequence. And so my common difference, the common difference here is 4. And so I can find the next 3 terms. 13 plus 4 would be 17. 17 plus 4 is 21. 21 plus 4 is 25. And that's 3 terms. So that is my answer. I didn't need that last little comma there. I should have just left it alone. That made it worse. Let's move on. Okay. So 81. 81 plus what is 27? Well, 81 plus it's going to be 60 something and or 50 something. And clearly if I negative 50, if I subtract 50 from 27, I'm not going to get 9. So clearly it's not arithmetic. So let's divide here. 81 divided by 3 is 27. 27 divided by 3 is 9. 9 divided by 3 is 3. Now we said division, but remember divided by 3 is the same as multiply by a third. So in this one we're going to have a geometric, and its common ratio is going to be a third. That's the same as divide by 3. So 1/3 times 3 was going to be 1. 1/3 times 1 is 1/3, and then 1/3 times 1/3 would be 1/9. Those are the 3 terms in that sequence. All right, Mr. McColley is trying to get back into shape. On day 1, he does 10 push-ups and increases the number of push-ups he does by 2 each day. How many push-ups will Mr. McColley do on day 14? All right, so this one here is a little bit misleading because your first thought is to say, I'm going to go since 14 times 2, that would be 28. I'm going to add it to 10. But when you're talking sequences and series, 10 is day 1. All right. That would be 12 for day 2. All right. That would be 14 for day 3. That would be 15 or 16 for day 4. And that would be 18 for day 5. I'm going to stop there because you get the gist. But notice if I said how many push-ups would he do on day 5, right? If we did that process and I said, okay, 5 times 2 is 10, 10 plus 10 would be 20. I'm actually would be too short here. So to solve this one, I'm actually going to reduce this by 1. And we'll see what happens with that in the next section and how that affect the general formula. But it's going to be 10 plus 13 times 2. So 10 plus 26 will give me 36 push-ups on day 14. All right. Well, that's all I got for today, folks. So the McColley fun fact of the day, since we have been on a longer extended break here during the COVID, I recorded this during COVID um, break, I have found a little game that I'm really enjoying right now. I like a Kerbal Space Program, and get these little guys, and you basically create little rocket ships for them, and you send them out into space and hope that they don't crash and burn. And I fail a lot. I crash a lot of times. So, but it's fun. You can get it on Steam. It's not a plug. They're not supporting me. I just like it. Have a good day. Bye.